Swayam Prabha. Digital India. Educated India.
Welcome back. In the last lecture, we started our discussion on the IP table lookup. We saw some of the data structures available for doing the IP table lookup in the software. Particularly, we saw binary trie and couple of optimizations on the binary trie. We'll continue that discussion today. We'll see some more optimizations that are possible on the binary trie. And also we'll also look into the hardware based IP lookup because software based lookup, as we said, is computationally it is expensive. Several memory references are required, and in order to speed up hardware implementations are also sometimes used. So the agenda is to basically, the first part we'll see the optimization, the binary trie based data structures, and in the second part we'll see the hardware based implementation for doing the lookup. So we'll begin by taking one more example of the construction of the multi-bit trie. So multi-bit trie we did discuss in the last lecture. Here is a set of prefixes that are given to us, particularly from P1 to P9. And he is asking to construct a 3-bit trie. So meaning every time you do a comparison, you do a comparison of 3 bits at a time. So as usual, if there are 3 bits, then the table structure will have entries for 3 bits at a time, and 2 to the power of 3 is 8. So every table will have 8 entries in total. So this is how the first level trie look like. The way, again, as usual, the construction begins by looking at the prefixes which are up to length 3. So that's where the first level table will have entries from prefixes from the P1 to P5. That's what is on here. And these are how things look like. From 00, all 00, if we have an IP address starting with 000, then this is routed with the prefix P3. That's the best match that you can find. And 001 is also matched with P3, and 010 is matched with P1, and so forth. And as usual, the best way to look at is how exactly this is routed, what prefix actually takes precedence over the other one, is to do the expansion and then cancel out whatever is the superset of the other thing. So P1 actually has prefixes from all zeros to all ones up to 3 bits. 010, 011, 100, 101, 110, and 111. So this is the set. All these IP addresses which are starting with 000, 001 and up to 111 are all matched with the prefix P1. So P2 will match with anything that is starting with 1. So 1, the 2 bits are variables, so that those 2 bits can be either 00 or 01 or 10 or 111. These 4 prefixes are matched by these 4 IP addresses which are starting with 100 and 111 or up to 111 are matched with P2, and P3 will match 00, and the next bit can be either 0 or 1. So these 2 are matched with P3, and P4 actually is 101. P5 is, that is actually 3 bits, so we are expanding only up to 3 bits, so that's okay. P5 is 111. So anything, if you get an IP address with starting with 101, then P4 will take the precedence over the other cases. So wherever 101 is appearing, so that will need to cancel it out. 101 is appearing here, 101 is appearing here, these 2 cancel out. And wherever you find 111, those the cases will also need to be cancelled because P5 takes the precedence over the other one. So this P5 is okay. So this 2 P4 and P5 are 3 bits, so those are given the preferences. And then a double 000 and 001 are given preference with P3. So this 000 and 001 will cancel out from the P1. Okay, one more thing is left. P2 also having triple one, so that will also get cancelled. And rest, I think 010 and 011, so none of them are out. So this is how the look like. So P4 and P5, P4 is here and P5 is here. So these two will take precedence. First you make entry for P4 and P5. Then you go to the P3, that is starting with 00. So P3 00 is here. So these two entries will be taking are routed with the prefix P3, and the P2 100, which is here, and 110, which is here. These two are IP address, any IP address with the starting with 100 and 110 is matched with P2, and rest of the entries are actually filled with P1. So that's the default prefix, any IP address is matched. That's how you figure out first level. You take, if you want to construct a k-bit trie, first expand up to k, look for the prefixes which are up to k bits or less than that, and then whichever the prefix which are less than k bits, you expand them. And then if there are prefixes which are of the higher order, which are subsets, basically if here in this case 3-bit trie wanted to construct any prefix which is having 3 bits in one go, first you give preference to them, and then the remaining you come to the next level, 2-bit prefixes, 1-bit prefix, and then finally the one which is the 0-bit prefix or the default prefix will take the precedence. So that's how you map the entries in the first level table. And now this should continue. So in the second level structure, what we will do is, so first 3-bit first level table, 3 bits are matched, and the next level table will also match another 3 bits. So prefixes which are up to length 6, greater than 3, but up to length 6 are now taken care, are going to appear in the second level table. So precisely P6, P7, and P8 fall in this range. So P6 is 4 bits, P7 is 5 bits, and P8 is 6 bits. So these are the entries which are actually falling into the second level table structure. And the way to go about it is, look at if any of the prefixes which are already marked or entered in the table level 1 structure are the supersets of these P6 to P8. And it turns out that P2 is a superset of all 3 of them, P6, P7 and P8, because P2 is saying 1 star. So 1 star will include 100 star also, 11101 star also, and 11100 star as well. And P5 is a superset of P7 and P8. P7 and P8. So these two, because P5 is 111 star and P7 is 11101 star. So we'll draw the entries in the second level structure by taking this order of the preference into account. So if you look at the structure, the second level structure would look like something like this. Since P2 is a superset of P6, 1 star, here in this case, if it is a 111 star, then we are going with the P5, but only 1 followed by something next level. If it is 0, then we have to go with the P6. So we'll draw a pointer from this P2 to the second level structure, starting with 000 and then 001 and something like that. And what we see is P6 is 1 followed by 00 followed by 0 star. So what it means is, if I expand this, so P6 will expand something like this. 100 is fixed, and then another 0 is fixed, but the next 2 bits can be either 00 or 01 or 10 or 11. So basically keeping these 4 bits intact, 100, I am varying the last 2 bits as per the commandment, and then For all of these cases, because all of them can be written as 100 star. So 100 is matched at the first level, and the next 0, this 0 would match in this level. Right. So wherever there is a 0, so in precisely in these 4 locations, the 4th bit is 0, and I don't care really what is the next 2 bits. For all those cases, I write them as the P6. So all of them are getting routed through by using the prefix P6. That is the best match that you can find for any IP address with starting with 100. Similarly, for the P5 is a subset of superset of P7 and P8, and as an expansion of the P5, a pointer from that in the first level table to the second level structure would have entries with the P8 and P7. So that's what is shown in this table structure. So from in the second table. So we can get that P7 is a 5-bit prefix, and P8 is a 6-bit prefix. So exactly one entry. So 111 is here, and 001 is actually in the second level is matched. 111 followed by 001 is P8, and again P7 is 5-bit entry. You expand that. P7 would include 111 followed by 01, and the next 1 bit can be either 0 or 1. For these 2 cases, 0, 1. So they varying this one for these 2 cases where the next what is that 6th bit is either 0 or 1. You mark those 2 entries with the P7. So anything that is starting with 111 followed by 001 or 010 or 011 will be routed with the within port number, whatever is the prefix P7 is actually telling you. So that's how the second level structure is constructed. And so we are done with the case up to P8. Now we need to look for the P9. P9 will appear in the third level table, and it is easy to note that P9 is a subset of P6. From the P6 we will go to jump to the P9. So P9 is 7 bits. We will need to expand that. P9 make it 9 bits. So 1000011, the 7 bits. These 2 bits can be either 0, 0 or 01 or 10 or 11. So up to these cases. So keeping the first 7 bits intact for all these 4 cases, I am going to construct these 4 prefixes will be matched with the P9. So as an expansion of the P6. So first 100 is matched here at the P2, and next 001 is matched at this location. So this is the precise location P6, and as a extension at the third level you will have from P6 to these 4 entries. What are those? 100, 101 and 110 and 111. These 4 cases are actually routed with the prefix P9. Whatever the port number P9 is telling, using that it is actually routed to the next hop. That's how the multi-bit trie is actually constructed. And just to summarize, what is the multi-bit trie? You look for all the prefixes in your routing table, and you decide what is the number of the bits that you want to match, and construct a table for k bits at a time. First level table will have only entries for 2 to the power of k number of the possibilities, and then the next level will have another 2 to the power of k number of the bits will be matched, and in the next level another 2 to the power of k number of the bits will be matched, something like this. So if your prefixes are not aligned to the exact match of multiple of the k bits that you chosen, then you need to expand that and fill the entries in the table. So that's how multi-bit trie is actually constructed. But every table entry will match only the k number of the bits. So that is one optimization that you can do on the binary trie. So where if you have the ability to match multiple number of the bits in one go, then you can do that. So now the question is it the only optimization that you can do on the binary trie? I have the ability to do the multiple bit comparisons, but what you can see is some of the entries in this table structure, particularly at the second level and the third level. So these 4 entries are left blank, and these 4 entries are also left blank, and these 4 entries are also left blank. So we are in effect every table entries in this sense in this table are basically are the pointers, and some of these pointers are not used. And by virtue of that, you actually end up wasting some of the space in the table. So every table has got, although it might happen that only one entry out of 2 to the power of k possibilities are actually having an entry, but remaining ones are actually not having an entry. Then, so the remaining 2 to the power of k minus 1 over the entries will be left empty. So that will end up wasting the space. So what the level compressor trie actually allows you to do is to have variable number of the bits compression. So meaning I can have a one level compression with the 3 bits. The second level compression can be with the 2 bits and so forth. I can do 4 bits, 3 bits, 2 bits, whatever is possible, wherever the compression is possible, that I am going to have embedded in the table structure. So let's try to understand how exactly this is done. So here is a binary trie, which is actually having some nodes. And an interesting thing to note about this binary trie is all the marking that is here. So for example, this is colored with the blue, whatever the nodes which are actually colored in blue filled with the blue color, those are the ones which are representing the prefixes. It indicates that a prefix is matched at that level, at that node. So one interesting fact about this trie structure is all the markings are at the leaf nodes. There is nothing which is at the intermediate node. For example, this node is not marked. So similarly, several other nodes, including the root node, is not marked. And it is possible to convert any arbitrary trie structure where the marking is done at the intermediate level to a trie structure where the marking is only at the leaf node. And the simple answer to this is how do the conversion is to do the expansion. So for example, if this node is something which is marking indicating 1 star, I can push this marking by doing an expansion, anything that is starting. So because the left child is 0 and the right child is taking the path of 1, this, if I mark this node that indicates a prefix of 1 star, so I can make this as match with the 3 bits by doing an expansion, 100, 101, 110 and 111. For all these cases, the nodes wherever these are matched, there I can do the marking. So meaning, so 1 star is not marked, but 100 is marked. So that is the node. This is the node that is indicating that. Similarly, 101 can be marked and brought it here. So like that, all the markings in the trie structure can be pushed to the leaf node by doing such an expansion. So in effect, any arbitrary binary trie that you can construct for some prefixes, for that there exists an equivalent trie structure where the marking is done only at the leaf node. So assuming you are given such a binary trie, and what level compressor trie does is it look for opportunities to compress the variable number of such trie structures, so bits, and merge into O. So the way to go about it is look for a complete subtree which is embedded in this particular trie structure. So for example, if you look at this diagram, and all these nodes starting from the root node, everybody has got two childs. This is 0 1 0 1 0 1 0 1 0 1 0 1 0 1. This is a complete binary subtree which is embedded, or which is a subtree of the original tree that we have. So what I will do is, wherever such complete subtrees are appearing, those portions I will look into, and then I will replace these entire set of subtrees with the as a descendant, direct descendant to the root node. So in this diagram, this is one subtree, and starting from this node, there is another substructure which is actually complete in nature. So it is 0 1 0 1 0 1. So every node has got two childs. This is a subtree which is actually again a kind of the complete tree. So now one level, the first level merging, I'll collapse all these 3 bits and make a direct descendant of the root node with 3 bits. And the second level, because this is also a complete subtree, I'll collapse this and make 4 descendants for this particular node, and then appropriately mark them. So here is the structure. So this is the node which is indicating all zeros. The path, leftmost path, what was existing here, 0 followed by 0 followed by 0, you are coming here. This is the node which is actually descendant of the root node. This is the node which is indicating 0 0 1. This is the node which is indicating 0 1 0, and this is the node which is indicating 0 followed by 1 1, and this is the node 1 0 0 1 0 1 1 1 0 and 1 That's how the first level marking is done. This is as good as having a table with the 3-bit entries, 2 to the power of 3 possibilities. And then in addition to this, and similarly I also collapse these this node. So this is the 0 0, this 0 1 1 0 and 1 1, 4 possibilities, because when you collapse a tree with the height of 2, then you will get these 4 possibilities. In addition to that, what I also do is, I will bring the concept of the path compressed trie. Wherever there is a node which is actually having a single path from that particular node, I am going to collapse all that and still remember what is the skip length and what is the skip value. So for example, this is the node which is actually 0 0 followed by 1, and I'll push this into this level and then mark that this is 0 0 1, and what I skipped is of length 2, and the value that, or the segment that I skipped, is a 0 followed by a 1. So this is done at the every level wherever there is such collapsing possible. So by doing the path compression, I am going to relabel the nodes which are actually representing the with the collapsed entries, what is the skip length and what is the value I am going to remember. So this is, you can think of level compressed tree is a combination of what the multi-bit trie is offering you, but in addition to multi-bit trie with a variable number of the bits at different levels, and in addition to that, whatever the single chain paths are there, those are also we are collapsing and making it as the and remembering what we have skipped and what we have what is the value that is skipped. So that's how the trie structure is compressed. So if you do this, then my height of the trie will also reduce. At the same time, I will also be able to do multi-bit comparisons and go. Not only k bits, fixed k bits, but variable number of the bits as well. So that is the concept of the level compressed trie. So this goes with an assumption that the router has got the ability to do variable number of the comparisons, sometimes 3, sometimes 4, sometimes 2. And also the data structure is able to store what is the skip value and segment that is skipped.